All right, let's take a look at the section 5.5 homework on the substitution rule. Right, so this first exercise, we're just doing an indefinite integral, so no bounds here. We're just trying to find our capital F function. Since the original function is given in terms of x, we're going to state our capital F function in terms of x as well. And in fact, they actually give us the appropriate substitution. If you didn't have this given to you, you could observe that the minus x squared is contained within the exponential function, which is a hint to the fact that your u ought to be the minus x squared, because that's what's inside the exponential function. That's one hint to the chain rule. And then otherwise, you could also notice that the x squared and the x were two bits that would be like your u and your u prime within your expression. So yeah, if u equals minus x squared, then differentiate both sides, you get du equals minus 2x dx. And while you don't have a minus 2x dx, you could just divide away that minus 2 to get exactly the x dx that you need. So, right, classic example, albeit they're giving you the u straight away. I guess similarly in number 2, they give you the u straight away, but whether or not you knew the u, because when you're working these substitution examples in practice, often you're not given the u, you sort of need to detect that the u is there. Well, you could notice that the x cubed plus 29 is contained within the square root. That's a sign of the chain rule having occurred. You've got a function inside a function. And moreover, you could notice that the x cubed plus 29 and the x squared are related in some way by way of derivative. Now, indeed, whenever you compute the derivative of both sides of u equals x squared plus, or x cubed plus 29, you'll get du equals 3x squared dx. And while you don't have a 3x squared dx, you have just an x squared dx. You can divide both sides by 3 to ultimately get the x squared dx as 1/3 du. So let your algebra do the talking, let your integration do the working, and you'll get an expression for the antiderivative in terms of u, plug back in terms of x, make sure you add your plus c, and there you go. Right, on this next one, oh gosh, they give us the substitution yet again. Even if we hadn't been given this x to the 5th minus 2 as a suggestion for the u, we could note that we've got an x to the 5th minus 2 and an x to the 4th. Those are related by the way of derivative. The u should be the x to the 5th minus 2. The du should be the, well, related to the x to the 4th. Incidentally, I believe du turns out to be 5x to the 4th dx, but that constant multiple of 5 can be adjusted. So ultimately we could divide that 5 away and get that 1/5 du is just x to the 4th dx. So right, that is that. Okay, so this next one, if you wanted to, you could FOIL this out and it would be kind of nightmarish. Alternatively, if you just let u equal the 3 minus 8x, that is beneficial. Note, the 3 minus 8x is inside the function of something raised to the 12th power, which is an indication that we've got a function inside another function. That's a chain rule thing. Alternatively, you could note that 3 minus 8x being our u means that minus 8 dx is our du. And while we don't have a minus 8 dx, we could factor that minus 8 away by dividing by minus 8, and we would get what? That minus 1/8 du is equal to dx. You can always substitute directly for dx, and well, then that means you could resolve this integral by letting u equal 3 minus 8x, and whittling down to the fact that minus 8 du is equal to dx. And so you'd have your algebraic substitution, you'd be able to apply integration in a straightforward manner, and that would be quite lovely. Here, boy, we've got a function inside a function, so to speak, here with this 5 theta. Makes me want to make that 5 theta be the u. If 5 theta is u, then du is just 5 d theta. And while we don't have a 5 d theta, we have just a d theta. That 5 can be divided from both sides of our du equals 5 d theta equation. And so it's going to take a little bit of algebraic manipulation to work this out, but I believe we will end up with 1/5 integral secant squared u du. And while secant squared u du may not be the most memorable integral from our past, it is a direct formula of one we've seen before, what the integral of tangent u would be secant squared u. That's a straightforward fact. And so the antiderivative of secant squared u du would be tangent u plus c. Since we have that factor of 1/5 in front, we'd have to account for that appropriately. Coming down here, another subtle one where it's not necessarily so obvious exactly what our u is, but if we do let our u be equal to the 2x plus 7, then taking the derivative of both sides of u equals 2x plus 7, we would get du equals 2 dx. And I don't love the 2 being in there because we don't have a 2 dx, we just have a dx. But if we divide by 2, we would then have a statement that 1/2 du is equal to dx. And that allows us to plug and chug. I think you'll end up with the ln function here. Don't forget your absolute values. It reminds you actually right here. Remember to use the absolute values when you get the ln function showing up. But hey, that's perfectly par for the course at this point. Also, don't forget plus c because we're just finding the general capital F function for the function that's inside our indefinite integral. Down here, this is what we did actually in class. So what we let u equal cosine theta because the cosine function is inside the function raised to the 6th, which is an indication that we've got the cosine theta as our inside function. The sine x will show up as the derivative of cosine theta, or rather the sine theta will show up as the derivative of cosine theta, because if u is cosine theta, then du is minus sine theta d theta. And while we don't have a minus sine theta d theta, we have just a sine theta d theta. If you multiply both sides of the equation, du equals minus sine theta d theta by -1, well, then you'll get that sine theta d theta, what's precisely within our indefinite integral, is just negative du. And that's good for business because I think this integral then becomes negative u to the 6th du, which is pretty straightforward to work on. Just remember, to give a proper evaluation for this indefinite integral, we ought not state our antiderivative function in terms of u. Rather, we ought to go all the way back to the original variable of interest, which in this case was theta. Coming to the next one, this one's a little bit subtle. There's occasionally subtle examples of the method of substitution. Here, what I notice is that I've got an ln x inside my something raised to the 8th. That's an indication that maybe ln x plays the role of our u. But of course, if ln x is playing the role of our u, then 1/x dx has to make an appearance. But observe that it does, because you see there's an x downstairs and a dx over here. So in fact, if you sort of broke this integral down, it would be ln x to the 8th times 1/x times dx. Because of course, if you took the ln x to the 8th and multiplied it by 1/x, the ln x to the 8th is upstairs, and you have exactly ln x to the 8th over x. So if you think of the x that's downstairs as like a 1/x that's being multiplied by your ln x to the 8th, it can be easier to see how the 1/x dx makes an appearance as our du, assuming that we let our u be ln x. So another nice, I suppose, example of substitution, albeit letting u equal ln x in this case, because that's our inside function. Okay, this example is probably the most complicated, and I want to take a moment to sort of walk through the process. Now, as I look at this one, at least initially, what I want to do is let u be equal to the 6x plus 7, because I don't want to take 6x plus 7 and FOIL it out 8 times. That's a nightmare. So what I want to do is let u equal 6x plus 7. Now, that's not the end of the world for a substitution in this situation, because assuming that u is equal to 6x plus 7, we could take derivative of both sides, and we'd have du is equal to, well, 6x plus 7 has a derivative of 6, and then we just park on the dx to use that notation, which works so nicely with substitution. Now, of course, we don't have a 6 dx in this function. We just have an x dx. But, well, hey, we at least just have a dx, so why don't we just divide by 6? So here we just divide by 6 and get 1/6 du equals dx. Okay, now at this point, we have what we need to plug in for dx. Dx is just 1/6 du. We also have what we need to plug in for u. U is just 6x plus 7. What we have yet to account for is this x that's on the outside. Because if we just apply what we have so far, let me sort of sketch this out. We would have integral x u to the 8th times 1/6 du. And now that 1/6 is not that bad. That's just a constant multiple that can factor out. What is in need of repair is, again, this x, because when we apply substitution, we want all the u's to go away, or excuse me, all the x's to go away and only u's to make an appearance. And so what we have to do is somehow get x out of this integral, and we need u in this integral. And you say, well, how do we do that? Check it out. The expression above u equals 6x plus 7 could equally well and good be solved for x. And if it were to be solved for x, please note, solve for x. What do we get? Let's see, we just subtract 7 from both sides. You get u minus 7 equals 6x. And then, well, solving for x, divide both sides by 6, you get 1/6 u minus 7/6. Dividing both terms on the left-hand side by 6. And this is not, perfect, I suppose, but it works, because if you let x be replaced with 1/6 u minus 7/6, you would end up with 1/6 u minus 7/6 times u to the 8th. And let's not forget that 1/6 du. And so if you distribute this all out, because now you just have this sum of things multiplied by u to the 8th, maybe I'll take the 1/6 and just factor that out. If I take the 1/6 and factor it out, 1/6 u times u to the 8th gives 1/6 u to the 9th. And then minus 7/6 times u to the 8th gives minus 7/6 u to the 8th. And then we still have our du out on the outside. But what you can observe is that this integral now is straightforward to compute. We're just utilizing polynomial antidifferentiation, which is only so bad. So as it turns out, we can find the antiderivative here. What we'd have this guy, this 1/6 u to the 9th would be 1/6 times u to the 10 over 10. And then the 7/6 u to the 8th would be 7/6 u to the 9th over 9. And so we can utilize that. Now, of course, written in terms of u, we'd still have to go back to x. So we have to replace the u's that result in our antiderivative computation with 6x plus 7. It would give you a clunky, cumbersome, lengthy expression, but that cumbersome, clunky, lengthy expression provides the capital F function by which we could assess the signed area between this function's graph and the horizontal axis. Admittedly, this is the hardest question from the whole bunch, but hey, we got some opportunity to discuss it, so I sort of feel better about that. Let's see, moving on from that hardest question, let's get back to definite integral here. Now we're using bounds. So actually we did this example in class today. So if you let u equal pi t over 2, then du would just be pi over t dt. And while we don't have a pi over t dt, we just have a dt, you could divide both sides by pi over 2 to get that 2 over pi du is equal to dt. Swap out dt for 2 over pi du, and then you'll just have 2 cosine u times 2 over pi du, and that's only so bad. Yeah, you could factor out the 4 over pi. If you would, you'd just be integrating cosine u. When you integrate cosine u, you just get sine u, but don't forget, when you plug in, don't plug 1 and 0 in for u, because 1 and 0 are in terms of t. So what we would have to do to plug in for u within our antiderivative function, which I think comes out to be 4 over u, or 4 over pi, excuse me, sine u, we need to change our bounds from t to u. And since u is equal to pi t over 2, plug in t equals 0, we'll get 0 down below, plug in t equals 1, we'll get pi over 2 up above. So u equals 0 and u equals pi over 2 are the bounds in terms of u, which are what we would have to plug into our antiderivative function in terms of u in order to get the desired result. Alternatively, if you want to take the antiderivative function all the way to t, you can, in which case you can just then subsequently plug in the t values of 0 and 1, and that would give you the exact same answer. In both cases, you get the exact same result. Looking here, right, they're suggesting to write the original integral as something to the 1/3 power, where that something is 1 plus 7x, which 1 plus 7x can take the role of our u. Now, the bounds were initially along the x-axis between 0 and 1, but along the u-axis, if u is equal to 1 plus 7x, then x being equal to 0 will correspond to u equals 1, and x being equal to 1 will correspond to u equal to 8, because 1 plus 7 times 1 is 1 plus 7, which is 8. So our bounds should go between 1 and 8 instead of 0 and 1 once we adjust in terms of u, which means when we look at our antiderivative function based on this expression, our antiderivative function should be what u to the 4th, or u to the 4/3 rather, times 3 over 28, I think, because 3/4 times 1/7 is 3 over 28. And well, then we just need to plug in our bounds. We had computed them previously to be 1 and 8, or rather, the cube root of 1. Well, no, the bounds were 1 and 8, and then we're going to plug in our appropriately to get the resulting definite integral value. So it's going to be a little bit tricky to work with that 4/3 power, but remember what the power in the denominator is the root, and the power in the numerator is a standard exponent. So if you have u to the 4/3 and you need to evaluate, you could first evaluate the third down below as the cube root, and then take the result and multiply it by itself 4 times. So that shouldn't be utterly terrible. For this next one, we're going to need to integrate the definite integral. Let's see. First, we would use u equal ln x, because ln x is that inside function. Letting u equal ln x, the 1 over x dx, would also take care of itself. Incidentally, I think your function becomes integral of u to the minus 1/2, because we have the square root downstairs. Powers downstairs show up as negative exponents. Roots show up as fractional exponents. So a root in the denominator would be a negative fractional exponent, as it turns out. And then whenever you integrate and you get whatever function that you do after integrating, you'll get something in terms of u. And to utilize our bounds here, since u is equal to ln x, we could plug in e and plug in e to the 4th to get our bounds, I believe, to be 1 and 4 in terms of u. So rather than taking our antiderivative function all the way in terms of x, if we alter our bounds to be in terms of u, that can provide us a sharper mechanism by which we can evaluate our definite integral of interest. Okay, down here, 13, what I want to do here is let u equal x squared, and if u is equal to x squared, then du is equal to 2x dx, which means x dx is just half of du. So, okay, hold on a second. I'm almost confusing myself saying all this out loud. Let me just snip this and give a little bit of work to help here, because this one is a little bit unorthodox, this question, but it is a good one. So, right, what we want to do here is let u equal x squared, which means what? Du is going to be 2x dx. Now, of course, we don't have a 2x dx. We just have an x dx. So what are we going to do? We're going to divide by 1/2 and get 1/2 du equals x dx. Now, the x dx becomes 1/2 du, which means this integral, which is between 0 and 4, the x dx is 1/2 du, and the f of x squared is then f of u. But now, how are we going to evaluate this this integral? Well, we need to swap out our bounds, because our bounds here were in terms of x, 0 and 4. Our bounds here need to be in terms of u. But you see, x equals 0, x squared gives you u. You have 0 downstairs. and x equals 4, square that, you get 16 upstairs. And so put this all together, our integral in this case is factor out the 1/2, constant multiple. You go from 0 to 16 of f u du. Right, forgive the profanity, I suppose. It's just a function of u. And yeah, here we go. 1/2 integral from 0 to 16 of f u du, which if integral from 0 to 16 of fx dx is 12, you can think about what we have here. We have exactly half of that, frankly, because the integral on the right is exactly the integral that we see here. So you guys can connect those dots at this point. This one here, you might think of your fx as your u, and if you would think of your fx as your u, then your du would be like f prime dx. Now, the only problem here is that this integral is between a and b, and so if you are evaluating, you would not get just the capital F function. You have to evaluate at b and evaluate at a and subtract, which is not what's occurring here. So if the a and the b were taken away, I believe this is accurate, but with the a and the b here, I believe this is false. Right. I don't know what their definition of area under the curve is. If their definition of area under the curve is the signed area between the function's graph and the horizontal axis, then yes. Can I pull up the? I don't know if I can pull up the key on this one to see exactly what their interpretation is, but I assume this is true. But yeah, it's hard for me to say exactly given what they mean by area under the curve. I suspect they're assuming that this is true. Where they mean that area under the curve is the signed area between the function's graph and the horizontal axis. Let's hope that's the case. I'm not where'd the bx go? That is strange. I'm highly suspicious this is false. I'm not sure where that bx term even went. Oh, is the bx term? Oh. This is slick, people. That bx term is a line through the origin, which means the area between 8 and -8 contributed by the bx term is necessarily going to be 0. Holy moly, this one is really slick. Let me show you what I mean by this. So my initial gut instinct was to say no, but I'm actually thinking this is true. So if we take this bit on the left-hand side here, and we look at it between -8 and 8, using our integration properties, we can separate the ax squared plus c from the integral from -8 to 8 of dx dx. So we're just using the summative ability of the definite integral. But if you notice, this guy has to be 0 because bx is a line through the origin. And when you look at a line through the origin, the area above and the area below necessarily cancel out when you're looking between -8 and 8. And so what's left is just this guy, but this guy is actually a parabola of some kind that's centered about the vertical axis. And so if you're going between -8 and 8, the area under it is actually going to be just twice the area on either side of the vertical axis by virtue of its symmetry. So here we're using symmetry to cancel out the bx term and to consider then this resulting parabola as well. The area under it is going to be twice the area between 0 and 8. Wow, that is subtle, but this turns out to be true. It almost seems like madness that bx term drops away, but incidentally, it is not madness. Here, if integral from 0 to 1 of f of x dx equals 0, well, all this means is that the signed area between 0 and 1 for this function is 0. That just means that the amount of area above and the amount of area below are 0. That does not mean that f of x is equal to 0. Well, yes, if f of x were equal to 0, you would have no signed area at all. The function's graph would be the horizontal axis, and you would evaluate to be 0. But if the area between 0 and 1 is 0 as the integral sees it, all that means is that the area above equals the area below. That does not force the function to be the constant function 0. You could have, as we saw in our previous example, some like this bx between -8 and 8. You could have some area region where there was an equal amount of area above and below that would cancel, which doesn't necessarily mean the function is constant at all. In fact, the function could just be a linear function, let's say like with an x-intercept of a half that was extending up at a slope of whatever it was. In fact, whatever the slope would be, if your x-intercept were a half, your linear function would satisfy this integral, which means, yeah, you certainly don't have to have the function f of x equals 0 to have an assigned area of 0 between 0 and 1. You just have to have equal amount of area above and below the axes. So if your area above and below is equal to 0, there's no guarantee that the function f of x equals 0. If this statement were reversed, if f of x equals 0, then your area is 0. Well, that's certainly true, because if your function was just a flat line on the horizontal axis, you'd have no area to consider because you have no height on any of your rectangles. But as this is written, because it is sort of like inverted, logically, the statement is false because, yeah, provided you've got equal amount of area above and below, you could have your integral evaluating as such, and your function not being just a horizontal flat line. Okay, so this might have been slightly longer than some of my previous discussions, but there were a few hairy questions in here, frankly. And hopefully what we've discussed has sort of helped clarify some of the hairiness, particularly towards the tail end. I hope this area in the curve one turns out to be true. If not, lo siento mucho. I did my best to try to interpret what they meant by that. Yeah, this guy is subtle down here at the end. This one's a little bit subtle. Yeah, we talked about the bounds showing up here, and that was kind of an interesting one here, number 13. That was kind of fun to work out. But yep, other than this, hopefully this can be helpful, and well, we'll stop it there.